So we would like to give the two very important theorems of elementary analysis that are direct consequences of the completeness axiom. Here, the completeness axiom is expressed through the fact that monotonic sequences that are bounded have limits. Also, we've seen that monotonic sequences are always can always be found within a sequence. So the first theorem that we would like to give is the celebrated Bolzano Weierstrass Theorem. This is almost immediate from the work that we have done in separate videos. And what it says is that every sequence, every bounded sequence has a convergent subsequence. So really, there's nothing to prove here, but let me just formally just say that let AN be a bounded sequence by the rising sun lemma it has a monotonic subsequence AN sub k, then this subsequence is monotonic and bounded, hence it converges. And that's all. So there's nothing more to add here. And we would also like to show the theorem that establishes what is usually known as completeness for a metric space, which is that theorem. Every Cauchy sequence converges. So proof, let AN be a Cauchy sequence. Then AN is bounded. Okay, how can we show this? Well, indeed, if we apply the definition of Cauchy sequence, we obtain N naught in N such that if M comma N greater than N naught, AN minus AM is less than 1. Okay, so we just apply the definition of Cauchy sequence for the number epsilon equals 1. Okay, then for n greater than n naught, we have that a n minus a n naught plus 1 is less than 1. Okay, because both numbers are less than 1. And that tells us that an minus an naught plus 1 is between 1 and negative 1. And finally, that an is between an naught plus 1 and an naught plus 1 minus 1. Okay, so pretty much all the terms of the sequence with finite many exceptions are inside this interval. All we need to do is just enlarge this interval so that it contains all the terms. And I know it's silly to try to do it formally, but let me just make such an attempt. So let me take m to be the maximum of a1 plus 1, a2 plus 1, all the way to a n naught plus 1 plus 1. Then we will have that an will be between m and negative m for any n in n. Okay, why? Because if n is greater than n naught, then it's this sequence that tells us that our number is between this number and its opposite. And if n is less than or equal to n naught, then basically what we're saying is that one of these numbers is less than ak plus 1, and it's greater than negative ak plus 1 minus 1, which is always true. So the bottom line is that a Cauchy sequence is bounded. And since it's bounded, it has a convergent subsequence. So since an is bounded, it has a convergent subsequence an sub k. Oops. An sub k. Let L be the limit of this subsequence. We will show that an itself converges to L, which is quite expected since an is Cauchy. That means that all of its terms come very close to each other. They come very close to the terms of the subsequence. The subsequence tends to L, so it pulls the whole sequence to L. So formally, how do we give this? Well, fix epsilon greater than 0. There exists n naught in n such that an minus am is less than or equal to is less than epsilon over 2 for n comma n greater than n naught. Then So that's the one thing. The next thing is that so here we have a couple of ways of doing this. We can say simply that this means that an minus an sub k less than epsilon over 2 for every n greater than n naught and nk greater than n naught. The sequence nk is strictly increasing, so at some point it gets greater than n naught. So here, if we fix n and we pass to the limit as k tends to infinity, so if, oops, sorry about this. So if we pass to the limit as k tends to infinity, then we get an minus L, which is the limit of the subsequence ak. It has to be less than or equal to epsilon over 2 for n greater than n naught. And of course, this means that an minus L is less than epsilon, which is all that needs to be established. So there are other ways to get this, but that's a very simple way. And that's something that actually we've seen an argument like this being used in proofs in the theory of Banach spaces. So that's all. Every Cauchy sequence converges. It's also a nice detail to note here that every convergence sequence is Cauchy. I mean, most probably you've seen that before, but let me just add it for the sake of completeness. Oops, I said completeness, right? But every convergence sequence is Cauchy. I mean, this is a very simple argument. So fix epsilon greater than 0. There exists n naught in n, such that an minus L, the limit of the sequence, is less than epsilon over 2 for n greater than n naught. And now if you take m comma n greater than n naught, then you will have that am minus an. You add and subtract L, and this is less than or equal to am minus L plus L minus an, which by the way is the same thing as an minus L in absolute value, which is less than epsilon over 2 plus epsilon over 2, which is epsilon, showing that for fixed epsilon greater than 0, there exists an n naught, so that for m comma n greater than n naught, we have am minus an. Oops, I erased here. Am minus an is less than epsilon. And that's pretty much it. This justifies why every convergence sequence is Cauchy. So Cauchy sequences and convergence sequences for the real numbers are exactly the same thing. Sometimes people wonder, why do we ever need the notion of Cauchy sequence? Do we ever need it practically? And yes, we need it practically many times, especially when we don't know what the limit is. So we cannot make direct reference to the limit, sometimes for theoretical purposes too. So yeah, that's all. But what is important to remember is that the completeness of real numbers through the fact that Cauchy sequences converge and the Bolzano Weierstrass theorem really show up in all important proofs in elementary analysis. Thanks for watching.